Good day, everyone. My name is Yerassyl Tursynbek, and today I'll present my project for the course Advanced Topics in Computer Network. The title of my project is SCEER, Secure Cluster-Based Efficient Energy Routing Scheme with Wireless Sensor Networks. This project is inspired by a science paper, but it's not a copy of that work. I studied the main idea, understood the logic behind it, and then implement my own version using Python. The main goal of this project is to design and simulate a routing method for wireless sensor networks that is energy efficient, stable on the mobility, reliable in data delivery, and includes security costs in routing decisions. During this presentation, I will explain why this problem is important, what solution I proposed, how I implemented it, and what results I obtained from my own simulation. Wireless sensor networks are used in many real-world applications, such as environmental monitoring, smart cities, agriculture, healthcare, and security systems. However, designing an efficient routing protocol for WSM is very difficult because of several fundamental challenges. First, sensor nodes have very limited battery power. Once the battery is empty, the node dies and can no longer participate in communication. Saving energy is always top priority. Second, in many scenarios, nodes are mobile. They can move because of wind, water, vehicles, or people. When nodes move, network topology constantly changes, and roads easily break. Third, unreliable wireless links often break. Interference, noise, and distance can cause packet loss or link failure, which reduces reliability of data delivery. Finally, sense networks often collect sensitive information. This data must be protected from modification, unauthorized access, which means security is also necessary. Because of these four challenges, energy mobile, reliability, and security, good routing protocol must consider all of them together, not just one of them. From existing research, you can see that many routing protocols have focused on only one main objective. Some protocols are energy only. They try to save as much energy as possible, but they ignore node mobility and link stability. As a result, routes often break, the network becomes unstable. Other protocols are security only, they provide strong predictable data but add a lot of overhead. This increases energy consumption, impactfully making the network expensive to run. So the real problem is that a single metric solution is not enough. We cannot focus only on energy or only on security. What we really need is a balanced routing solution that considers energy efficiency, stability, reliable, delay, security at the same time. Now let us briefly look at previous routing approaches in wireless sense networks. First, there's LITch. LITch is one of the earliest cluster-based routing protocols. It selects cluster heads randomly and rotates them in different routes. This helps balance energy, but because selection is random, it can choose weak or unstable nodes, which cause early failures. Second, there are energy-based routing protocols. In this method, cluster heads are selected mainly based on residual energy. Nodes with high remaining energy become leaders. This improves network lifetime but ignores node mobility and link stability, so routes can still break. Third, there's secure routing protocols. This focuses on protecting data using authentication and encryption. They increase reliability and trust, but also add extra overhead in terms of energy and delay. Finally, the SCEER idea combines multiple metrics. It considers energy, stability, distance, and security together. This makes routing more balanced and reliable. My project is inspired by the SCEER idea, but I re-implement it in my own way using Python and my own simulation setup. In this project, my goal was not to copy the original SCEER protocol line by line. Instead, I used it as inspiration and built my own version from scratch. First, I wrote my own implementation in Python. All clustering, class head selection, routing, energy update, and isolation logic were coded manually. Second, I created my own simulation environment. Nodes are randomly deployed. They move, consume energy, and communicate through multi-hop routing around network. Status update, just like in a real sensor network. Third, all results you will see are produced by my own simulation graphs are not taken from any paper. They're generated from my code using real simulation data. So this is SCEER inspired model about the design, implementation, simulation, and the results are fully mine. This slide shows the full workflow of my method step by step. First, we deploy the sensor nodes randomly in the area. Each node has an initial energy, position, and mobility model. Second, the network is divided into clusters based on distance and neighborhood. Nodes are grouped so that communication inside a cluster is short, range, and efficient. Third, in each cluster, we select the cluster head. Selection is not random. It's based on multiple metrics such as residual energy, stability, and distance. Next week, nodes are isolated. If a node's energy falls below a threshold, it is removed from routing to protect network lifetime. After routing is performed, data flows from member nodes to the cluster head and then from cluster heads to sink using multiple paths. Final security is applied at logical level. We add authentication fields, extra overhead, and packets which increase safety, but also affects energy and delay. This slide explains how the cluster head is selected. First, we calculate the cluster metric, where RE is the residual energy of the node and IE is its initial energy. This shows how healthy node still is compared to its starting battery. But energy alone is not enough, so we calculate a final score using factor score equals energy plus stability plus distance. Energy means how much battery the node still has. Stability means how the node changes its position or links. Distance means how close node is to the cluster center and to the sink. Node with a high score becomes the cluster head. This way, the CH cluster head is not only powerful but also stable and well positioned. Routing strategy. This slide shows how data is routed in our SCEER inspired system. First, normal sensor nodes send their data to their cluster heads. In this short distance transmission to save energy. Then the cluster head forwards the data to the sink. If the sink is far, the CH use multi-hop routing through relay nodes. Relay nodes are not chosen randomly. They are selected based on three main ideas: Cantor, nodes with high remaining energy are preferred, so weak nodes are not drained fast. Deliver paths with low transmission delay are chosen to make data arrive faster. Stable relay nodes that move less and keep stable links are selected so routes don't break off. And so the final route is not just choice only, but one that balances energy, delay, and stability. Now let's talk about security overhead in our system. SCEER-inspired routing. Every data packet is not sent alone. It's added with an authentication field in our simulation. We model this as an extra 128-bit security tag to each packet. This makes the packet slightly bigger, so two things happen. First, it consumes extra energy because sending more bits means the radio works longer. Second, it causes a small extra delay because processing and forwarding a larger packet takes more time. So security is not free, it also has a cost, but it's cost acceptable because in many wireless sensor network applications like healthcare, military, or smart infrastructure, Data must be protected from fake nodes and attacks. Our goal is not to remove security, but to control its impact. That's why in our meta security is combined with anywhere and layer routing. So even though we add secure overhead, we still try to choose routes that are efficient, stable, and energy saving. In short, security adds extra energy use and extra delay, but network becomes much safer and our algorithm is designed to balance this cost intelligently. I'll explain our simulation setup. We create our own simulator in Python, not just showing rows, but actually simulating how nodes, clusters, and roads behave step by step. First, the network area is 1,200 by 1,200 meters. It's larger, so multiple routing is necessary to reach sync. Second, number of nodes changes from 50 to 400. We will see how the protocol behaves in small, medium, and dense networks. Each node starts with 0 to 5 of initial energy, 0.5 of initial energy. Every transmission, reception, security operation consumes energy based on distance and packet size. We compare three protocols, which as a classic random classified selection baseline, energy-based routing. The classifier is chosen mainly by remaining energy, and SCEER inspired our multi-metric method using energy, stable distance, and security. All protocols are tested on the same conditions so the comparison is fair. Only the routing and classifier selection logic changes. This step allows us to clearly see how different strategies affect energy consumption, lifetimes, delay, stability, and reliability. Now I will explain the performance metrics that we use to evaluate our protocols. We don't rely on only one result because one metric alone can't show the real network behavior. First is network lifetime. This shows how long the network stays live before nodes start dying, measured by counting how many nodes are still live all time and also by checking moments like first node dies and half of nodes die. Second is energy efficiency. This calculates how many packets are successfully delivered per unit of energy. High value means network use battery power more wisely. Third is reliability. It shows how many nodes are routes successfully deliver packets without failure. For stability, it measures how stable network structure is, especially how often class heads change, cluster heads change too frequently, routing becomes unstable and wastes energy. Finally, delay. This average time packet needs to travel from a node to the sink. That includes transmission time, hop delays, and also extra delay caused by security operations. Using all these five metrics together allows us to clearly compare ledge energy-based routing and our SCEER-inspired method in a fair and realistic way. Now I will present the main simulation results. Here we compare three protocols, ledge energy-based routing and our SCEER-inspired method. On the left graph, we see network lifetime versus time. The blue line is ledge, the orange line is edge-based routing, and the green line is SCEER. We can clearly see that ledge and edge only routing goes nodes very fast. After about 30 to 40 rounds, most of the nodes are already dead, but SCEER keeps many nodes alive for a much longer time. Even after 200 rounds, a large number of nodes are still working. It shows that SCEER distributes energy consumption more evenly and avoids early this. On the right graph, we see node reliability versus number of nodes. Reliability means how often nodes and routes work without failure, which and energy-only routing have low and stable reliability. Values change a lot when the number of nodes increases, but SCEER stays much higher and more stable. It's because SCEER selects class heads using multiple factors like energy, stability, and distance, not randomly. So from these two graphs, we can see clearly SCEER lasts longer and is more reliable than the baseline. Now, let's look at the stability analysis. The graph shows node stability rate versus post time. Post time represents how long nodes stay still before they move in, so this graph helps us understand how mobility affects the network. Blue line is ledge, the orange line is energy-based routing, and the green line is zero. We can see the ledge and energy-based routing change a lot on both time changes. Their stability goes up and down, which means cluster heads change frequently. Frequent cluster head change cause more overhead, more control messes, and more energy loss. But green line, which is here, is much more stable even when post time changes. Stability radius stays almost at the same level. This means here is less sensitive node movement. Why does happen? Because here it doesn't choose cluster heads randomly or using energy. It also conserves the distance. So it avoids selecting nodes that move too much. This slide shows a trade-off between energy efficiency and packet delay. On the left, we see energy efficiency versus number of nodes. As network becomes larger, all protocols deliver more packets per joule, but SCEER stays close to best result. It's slightly lower than pure range-based method, but still much better than pitch. This happens because SCEER also considers stability and distance and all energy, so it avoids risk of unstable roads. On the we see packet delay versus speed. SCEER has little higher delay than the other two methods. This is because it checks more conditions: energy, stability, distance, and security. So random decisions take slightly more time, but KD is this SCEER pays a small cost and delay to get big benefits in lifetime reliability and stability. That's why the message of this slide is small cost for big benefits. But here is not just theory or copy formulas, I wrote my simulation code in Python to implement the idea of SCEER. In my code, I explicit model, node, creation with position, engine, mobility, cluster formation based on area and distance, cluster selection using multimetric score, isolation of weak nodes when energy drops below thresholds, routing from member, cluster sync using multi-hop, secret overhead to add to each packet. For example, when the program runs, it prints logs like which nodes become class heads, which nodes were isolated, which node was chosen, like sync how much energy was used on each hop. So I can clearly show this node become class head because it had high energy, good stability, and short since this node was isolated because its energy dropped below this threshold. Shows was chosen because it minimized energy and delay. This proves that SCEER is not just concept in slides, it actually works through real code, real routines, and real logs. That's why I say it is not a demo animation, it's work in simulation. So, to conclude, this project shows that a balanced routing strategy really matters in wireless sensor networks by combining energy, stability, distance delay, and security. SCEER inspired methods and weakness of single metric approaches. From the simulation results, we can clearly see there's three main improvements. First, network lifetime increases. Nodes die slower because the load is distributed more fairly and weak nodes are isolated. Second, reliability improves. Packets are delivered more successfully because roads avoid unstable or risky nodes. Third, stability increases. Class heads change less frequently, and when nodes move, which frees overhead and saves energy. Although SCEER interests small, extra delay and the cost to the security and multiple decisions. This cost is very small compared to the big gains in lifetime, reliability, and stability. So the final message is simple: a small increase in complexity gives a big improvement in network performance. And most probably it's not just theory, I implement in real code, test it in simulation, it showed real results. With each work, there are three clear directions to improve this project. First, the simulation can be moved to NS3, provides more realistic wireless channel models, behavior engine models. Second, real cryptographic algorithms can be added in this project. Security is modeled logically with extra bits, delay, and energy costs. In the future, can implement real encryption and authentication. Third, one can be tested on real sensor hardware by using real sensor, like Arduino, ESP, or Telo SB modes, we can validate whether routing schedules works in physical environments. So this project is strong simulation, proof, and the next step is to move from simulation to real systems. Thank you for your attention.